Well, I want to start by saying what a huge pleasure it is to be here to give a talk associated with the 25th anniversary of the Biocomposite Centre. And I think that's a tremendous achievement. There are a few people in the room here, more than I expected actually, who were there at the beginning. Dave and Gwen. And we actually gave it 25 days in those days, not 25 years. So I think it's a fantastic, I want to emphasize what a fantastic achievement is for a group, an institute that has been mostly soft funded all the way through its being, to have achieved so much, to have sent so many people around the world. Because everywhere we go in conferences and on my circuit and other people's circuit, I meet ex-Bangor BC people who are associated with BC, running institutes, running conferences, running cost actions, and all of them started here. So I think we should acknowledge that. And I think sometimes BC under-publicizes itself because some of its achievements are absolutely tremendous and are worthy of being blown up and publicized. And I think some of the contributions to biotechnology and, if you like, pragmatic biotechnology are understated. And in this talk today, I want to just give a little bit of the past. Yeah, thank you. I would like to just a little bit of the past, just to give a little bit of the beginning, because some people are not aware of what went on. Then I want to talk about not the details. I'd like to just to briefly describe some of the early research projects we have, and then I would like to move a little bit and highlight two areas that I think that BC have contributed hugely to the area, but haven't really been acknowledged. So I'd like to correct that. And then I'm very keen on the technology transfer site here in Mona. I have a company, we work there, and I see this as a great vehicle for the future. So I want to talk about that as well. So let's get on with it. But when I first, nothing's changed, you see. When I first looked at this talk, when I first thought about this, I thought, Biocomposites, a little bit biblical in a way. Because we can use a Bible model, so I thought this through. I thought we have the book of Genesis, and then we had James Bolton coming back from FPL in Madison and talking with Dave, and then we had Roger Cooper and Bart Banks, and this thing just came out of nothing. There will be a centre, and suddenly it appeared there was a centre. It was just like that. And it's not as simple as that. And then we could have the book of Numbers, where we have all the troubles and the strife and building the centre and everything that's gone on since. And actually we had some prophets. We had a management board, which were many prophets of doom, but they were there, so that's the biblical connection. But they've been proved wrong. But then I thought, no, there's the book of Revelations. And there we don't go there, because that's just too much. And then the extension of that is that then at some stage we bumped into the concept of having a Messiah. And I think even Rob would stop at that. So let's get back to it. So in the beginnings, and a lot of people, I might have some facts wrong, but let's get there. So there we go. So it was set up in 1809, which everyone knows, with a grateful help of the WDA. And it was largely in response to a call for new centres of excellence, but also the fact that the industry that we worked with, within the Wood Science Group, needed somewhere to do pilot work. The same as today, but in a more condensed way. And to improve links between the university's industry. And I think the main driver was definitely James Bolton, who's not here today. But I mean, Dave, you were plotting with him, I think, at the time, probably. And then, and I think James was largely inspired by going to FPL in Madison and seeing their pilot facilities and the way they did business. So he came back, and at the same time, James came from the Wood Science Group within Forestry and Wood Science, and there are many players in that group, and many are in this room. And I'll mention Bart Banks, Prof. Bart Banks and Roger Cooper. And I'll also mention Wood Tech, which was a group that they set up within their Wood Science department to actually have as a small unit to exercise this kind of industrial collaboration. And that was run by Harry Earle, a friend who's sadly absent. And a lot of us were friends with Harry, and Dick Salisbury here, he was part of that Wood Tech group. And they had a number of projects on chemical modification of wood preservatives, and wood treatment. And then, so 89, James came back, and there were a lot of discussions. But basically, the centre was established, and the MDF pilot plant, which a lot of you are familiar with, was installed and commissioned. The labs were developed. We took over the Adobe building, the old Adobe building, which is now flattened, and we incorporated the wood tech group, and then I think it was maybe you, Dave, who negotiated quite a crafty dual status, where we could have a sort of a university and research institute and centre of excellence, which was very clever and useful to get funding. And I think, just to recall, this was the original structure. Then we had our management board, our profits, and then we had James, and then we had 4 research groups. Dave was looking after wood physics, I was looking after the natural products chemistry, Harry was looking after, if you like, the process, and Walter Rankenholm was looking after the pilot plant. And I think that kind of structure has been maintained through Biocomposites, not the same groups. It's been rearranged many times, but they've been targeted specific project teams. And then Sue Knowles, again, who's no longer with us, she was in charge of publicity, and she did a very good job. So that's the beginning. And I think it's interesting to look at staffing levels, because we started with, I don't know if 4 to 9 is right, I mean, maybe 3. In 1996, when I left, we had about 50 employees, which is a lot. And I think it's all soft-funded, which is pretty astonishing to maintain that number of people on soft funding. And it's been the same, up and down, up and down. I think now, Rob, you're around 38, I think I read in the report, which is very impressive. And then I think we have to put up the Rogues Gallery. Let's get it done. So here we see the directors through the years. And I think you see them all, James, Jamie, Jeremy, Paul and Rob. And I think that each director has contributed in a significant way to developing the centre and making things happen. So I think they all need to be complemented in various ways. And Rob is leading it forward at the moment. So let's get on to some early projects. And I think I'll mention that the first couple of big projects that we had were link projects, which we call Link 1 and Link 2. And they had long titles, which I've dug around for. And for Link 1, I can't find the title. But it was all about improved composites and some chemical modification of wood and fibres and improved resins for composites. Link 2 was about straw fractionation. It was actually called multi-use approach to serial straw fractionation using thermomechanical refining. Remember that one? And these projects really got us off the ground in terms of R&D. And then also we got very good early on at writing EU applications. So we had a big project called RenewPack, which was a huge project at the time. I think it was the biggest EU project running at that particular time. And then there was Blow Dry, which was about blow line blending on the MDF line. And then we had another one, which is High Performance Biocomposites, which was run with Runa Simonson's group in Chalmers, which was all about wood fibre modification. And I recall that we also had 2 craft projects, my favourite projects, which were all about latent hardness for board resins and also annual crops. So we were within this area of wood modification, wood valorization, and annual crop residues. And also, I think another thing I haven't mentioned is that the centre was very much instigated also as a response to the crops for industrial use at the time. So back in the end of the 80s, the 90s, we were producing too much food. We didn't know what to do with our land. So there was this initiative to find new uses for crops. And a lot of our work was also looking at alternative fibres and fibre alternatives to fiberglass, to carbon fibre, and in biocomposites. I should mention that. Now, I'm not really going to mention the industrial clients because that's confidential, so I concentrate on what was the R&D. But also, we're all aware that BC very much works with one-to-one with industry and a number of projects, and a lot of project funding comes from that. So then, I should also mention the conferences, EPS and IPS, and I'd like to say that we first started talking about a conference when I was there in 91, and I remember I said, I think it's a stupid idea. Yes? Because we're too busy. And I think Dave was there, and I think James was there, and a few other people, and basically the decision was made to go ahead. So I was completely wrong, because these conferences have been very successful, so I was utterly wrong, as usual. And the first conference, EPS, was held in Llandudno in 97, and I think it was very well received, and the series went on. I think it was annual at that time. I think it was a yearly conference. And then it transferred to IPS International Panel Symposium in 2007 in Cardiff. And I think now it's a biannual conference, with an IPS masterclass today is the other side of that. So I think it's been very well received. It's been extremely good for publicising the centre and also for overall networking. So what I'd like to do now is just then move on to some of the research that I think is understated in BC. And I think that the work that was done with Dick is in the room here, for example, on acetylation of wood fibres. And for those of you that don't know about it, it's a modification of wood fibre that makes the wood fibre very water resistant and durable. And in BC, we were very, very good at chemical modification. The wood science department at that time was very good within BC. And I think that we were asked, and this came from the Wood Tech group, we were then asked to develop a full upscaling of this technology with BP Chemicals, and also with Acell acetyl cellulosics, which was actually the two main developers of acetylation technology recently, which was Runa Simonson and Roger Ryle, who we affectionately know as the two profs. So they were the two profs. And the goal was the continuous acetylation of MDF fibres at pilot industrial scale. It's quite a challenge. And I think that at BC, I think we could do 100-litre modifications. And there was a pilot facility in Hull where they could do a little bit bigger. And I think there were some tremendous developments in that project. And really, I think that a lot of the production that you see now out of Titan Wood, especially their fiberboard, is based on this, because the development work was done here. BP at the time when this work was completed, there was a little recession, familiar story, so they had to pull out. But then the guys, you don't need to say this, but just for those who don't know, you get tremendous water resistance from acetylated fibres if you make a board. It's really quite spectacular. And actually, acetylation of whole wood is difficult, but acetylation of fibres is not difficult, because it's quite easy to clean off the excess acid, and you don't have the same issues, but it's still not really commercialized. But the guys from Acell then built this plant, first pilot plant, based on the results from Bangor. They then built this plant, which was the first pilot plant. And I then in the early part of in around 2004 to 2006, I then worked very closely with Runa Simonson on designing the second plant. But then there was another recession, 2008, so that was abandoned. But the findings from this have been taken up now by Roger Ryle, one of the two profs, and he's now working with Titan Wood. So I think that you can see commercialization of this, and BC should take some credit for this, because the fundamental work was done here. And then I think the other area I'd like to flag up was our old friend, for those who were familiar with Sun, Runcan's son. He arrived as a PhD student for Prof. Banks, Port Banks, and I was his industrial supervisor here in BC, or the BC supervisor. And basically, Sun came along and he did an awful lot of very, very detailed work on the structure of cereal straws. And he went right into detail. He took it apart with a comb, looked at everything, extractives, polymer structure, lignin, hemicellulose, and analysed it to death. A little bit too much, it seemed at the time, because he went on, but still, very important. Detailed, careful, systematic analysis. And I apologise for putting a molecule up after 6 in the evening. So if you're a chemist, if you're not a chemist, look away. If you're a chemist, don't look too closely. But I think the important thing is this work resulted in an extremely precise characterization of the structural component in the cell wall. In particular, it resulted in an estimation of the number of ester bonds and ether bonds, the ratio, and how these things are how these things go, the quantification. And believe you me, if you're into second generation refining of straw, you need to know this. Because if you don't know this, you can't get the cellulose out. You can't take the hemicellulose out. You can't remove the lignin. You have problems. And he did a lot more than that. And I was there till 96, and he carried on with a lot of the guys. But basically, he documented several viable routes for wet fractionation of straws and other non-woods. And these results and findings have been used by biorefiners worldwide. I was at Novozymes, 3 or 4 years ago, and they had all of Sun's papers, and some of mine as well, because I was a co-author. And they had them all there, and they quizzed me on them because they're using this data to actually devise their straw hydrolysis. That was quite, and BC have no credit for that either, not at the moment. So I think we should note that one up. And we're still collaborating with Sun in Beijing and Guangzhou. He runs 2 big institutes there. And in this kind of roundabout way, it kind of leads on to this, it led me, the findings from that study, the wet fractionation, how you do it, led me into another branch of work in Scandinavia, which is about oat bran fractionation and how we take valuable things out of oat bran, but I'll come back to that. So, the middle years, I wasn't there. That's easy. But I flagged up a couple of big projects. BC carried on developing projects. I haven't really mentioned a lot of projects that you did in composites and looking at hemp fibers, flax fibers, non-wood fibers. But you'll have to talk to the other guys about this. But I'll flag up 2 big projects, Chemowood and Straw Frac, from that time. And I think also in that time, importantly, and maybe you didn't say at the time, was actually moving the pilot facilities out from Bangor to Mona. And in my world, you don't have a pilot plant in the middle of a town because you want to do some serious stuff. You have to transport things in and out. You make noise. You have dust. You have some emissions. Not in Mona, but in most pilot plants. But into Mona went the creation of BC Tech Transfer, and into Mona went the MDF pilot plant. The existing pilot facilities were transferred to Mona. I know it took some time to get them in. Resin development, extrusion, upscaling of chemical synthesis, to name a few. And since then, the last 2 years, you put in more. But again, I'll return to that in a minute. So Mona is excellent. But let's get to current BC and a little bit about, I've stolen this from your report, so you can check it out if it's wrong. But you have the funding from many, many sources, and it's like this, but it's still like that. EU, Welsh government, which is in my time, we had no Welsh government funding. UK, and then you have your direct commercial income. And you have made a strategic decision, of which, and I'm involved in a couple of bids, and other people are involved in bids to Horizon with BC for Horizon 2020 funding. And networking, and I'll come back to that, but networking is a very important aspect of BC activities. And I think I've pulled these 2 figures, £700,000 in capital investment in the last 2 years, and a lot of that's in Mona, and 2.4 million in research funding, so it's very impressive. And you're currently involved in I've looked it up, 3 EU FP7 projects, because it's in your annual report. Yeah. It's EcoC, improving air quality, buildings. BC Godos, is that correct? Yeah. Microalgal valorization. And I'm also involved, I know you're looking at macroalgae, so I'm involved in another small project there. And Brigit, bio-based resin system for composites. So these are current FP7 projects which are running. And hopefully soon you'll have a barrow load of Horizon projects to add to the list. So then, just to get into the future a little bit, I'm quite excited about the Biorefining Technology Transfer Centre in Mona. And my company, Beaumaris Technologies Limited, we are doing some trials there within the centre, using the new pilot plant. And you can read that, it's in the report, but I mean, upscaling specialities, technology transfer, especially in added value biorefining, I'd say, and utilisation of materials. And it's a dedicated facility for development of chemicals for the benefit of the low-carbon society. So then, into Mona recently has gone a wet fractionation pilot plant, which I'm very familiar with. So we'll come on to that in a minute. A pulp moulding plant where we can take fibres, and pulp moulding is a very old technology, but there's a lot of, with the advent of biorefining, there's a lot of fibre coming out. What do we do with it? We have to do something with it. And it's pulp moulding is a great outlet for bio-based and eco-friendly packaging material. And I think this area is quite a big area for BC at the moment, Rob. Or it could be. And then, of course, you have your supercritical CO2 plant, which is not in Mona, is Ray Marriott, and I think that's also thriving. But I think the supercritical CO2 is more for the high-end market. It's quite expensive, but it's very versatile technology, whereas the wet fractionation is more for bulk development. So here's the wet fractionation plant in Mona, and I'll just, some of you may have seen it, but basically it's, you can see there's 2 tanks on the right-hand side, and they're 150 litre tanks, and there we can put in biomass and water, and it has a big stirrer, and then we can add enzymes, and then here we have something called a wet mill in the middle, which you can't see, which actually does mixes the enzymes with the fibres and or with the biomass, and allows the enzyme to do their work. And then you have a heat exchanger, which allows us to control temperature and to switch enzymes on and off. And then the other side, you can see we have a continuous centrifugation. We have a decanter there, which allows us to continuously separate. And we have a separator at the bottom there, which you probably can't see very well. It's a continuous centrifuge. So that means we can take in biomass, we can process it using enzymes, we can split it into fractions. And the temperature control we have in the tanks allows us to be very, very precise. And if we use very specific enzymes and very targeted wet milling, we can do quite a lot. And this brings us to, and so we have a sort of base wet fractionation process. This might look simple, but I think this is the way forward. And I'll tell you why in a minute. And we mix biomass with water, so it's green chemistry, water-based. This is the critical bit, we use selected enzymes. So that we take a helicopter over the material. We say, what do we want out of this material? If it's a cereal bran, we want the soluble fibers for the food industry. If it's olive waste, we want to extract some phenolic component as a nutraceutical. And then, so that's where the money is. So we say that's where the money is, so then we choose our enzymes to attack other parts of the residue that's not going to destroy our function. And then we do a hydrolysis, and then some wet milling, and then we deactivate the enzymes using heat, and we then take these through a separation regime. And that's usually continuous centrifugation, because if you make a slurry such that your components that you want are not destroyed, they will then separate quite easily in a downstream separation process. This is principles of biorefining, and you don't end up with a soup. Because what you don't want is, and a trap many biorefiners jump into, is that they say, oh, this is a residue, look at those sugars in here, take it all. They hammer it with enzymes, they hammer it with acids, and you end up with lots of small molecules. And you can't separate them, not possible. So you have to take the approach that, let's leave some structure intact, and let's split it in a very cost-effective, cheap, fast way. And then when we get our pieces out, we can then smash them up if we don't want them. We can burn them, but then we have to have this kind of process to valorize the biomass. And these are advantages. That's actually beta-glucan, it's not cocaine in the spoon. Well, you don't know, but it's beta-glucan from oat. It's an so it allows you environmentally friendly processing. You can get very high value products from biomass. No chemicals, no byproducts, because you use everything. And then no emissions and a very good economy. But I think this is the key, increased value products. And I'll just go a little bit into fractionation of cereal brans, because this is something we developed. When I left BC, I was a professor in Copenhagen for 5 years. I got bored. So then I went into industry, working with a group of entrepreneurs, and we were looking at how to take cereal bran apart, how to make sugars from cereal bran, and how to get soluble fibers out. And we developed a very, very nice technology, which is just last year or 2 has been sold to Tate & Lyle, and they're now running the technology in Sweden. But this is a good principle of how we can use that pilot plant. And in this, you can see that here's a cereal grain, and in the middle you have the flour. The endosperm is the flour. If this is a wheat grain, you'd mill the flour out, and the bran would go to the animals. Yes, animal feed. If you're making bioethanol, you might take the whole grain, mill it up, convert the starch to ethanol, to glucose, and then to ethanol. But then that's fine. But there's no economy in it, because what you're left with after you've converted your starch to ethanol is a very low grade, DDGS, grain solids, which has no functionality, degraded proteins, degraded soluble fibers, and not much use for anything. So we took step back and we said, okay, and this is for oat grain. We developed technology for all grains, but we said, okay, if we take oat grain and we mill it as if it was wheat, so we mill out the flour. We don't want the flour. That's a byproduct. And then we end up with a coarse fraction of bran. And in that bran are all the goodies. So in this germ, you have all of the proteins and the oils that you can sell into the food market. And these cell walls here are soluble fibers, hemicellulose but soluble fibers. So if you want to be healthy, you need soluble fibers because the arabinoids, beta-glucans, they're good for digestion, they lower cholesterol, they have a manifold health benefits. So actually, when you look at a cereal grain or cereal bran, you actually want the soluble fibers, you want the oils and the proteins, but you don't want the starch. That's just starch. That can go for food or flour. So then we developed this process where we took out the bran, a coarse bran, and we ended up with a cereal bran. The flour is a byproduct. The hull will fuel the process. We burnt the hull. And then we took the oat bran and we mixed it with a specially cocktail of enzymes, which is a very special cocktail. And we then put this in the tanks like you see in the pilot plant, hydrolyzed it, mixed it, and wet milled it. And then we prepared a slurry, which you could then very easily split using continuous centrifugation into 4 very valuable fractions. Sorry, 3. Oat dietary fiber, which is insoluble fiber from the bran. Beta-glucan, which is soluble fiber, which sells for 25 or 30 euros a kilo into the food business. And the protein and oil. There's a protein shortage right now. So that protein is now selling for 8 euros a kilo. And the principle that we had to look after was actually maintaining structural integrity, so we don't destroy anything that we want as a value component. And that's about selection of enzymes and regime, and then we can separate. And this I'll give this glucan as an example. It's a soluble fiber, but it's a very nice ingredient for food, and it sells very well. But I won't be long. But basically, I put this up as a kind of challenge, because this is how I think a biorefinery should, or certainly an added value biorefinery should be yielding. And this is something that that process that we developed. If you take 70,000 tons of oat grain, and you buy in the oat grain and you make bran, and then if you look at the operating costs there, the actual price for the bran would be 100 euros a ton. And that's the price they sell it also out into the market. But if you do this kind of wet fractionation, you can make a ridiculous amount of money. I mean, you can't do this with every residue, but this is an opportunity. And the way that you do this is you do not destroy the useful functionality during the refining regime. You extract everything you can, and then the waste product you'll see is the maltodextrin, is the starch, which if you're trying to make bioethanol, that's the main product. It should never be that way. It should always be the byproduct, in my view. So then we built that plant. And this is a small version of that plant. So the plant in Mona is actually a small version of that plant. It's the basic unit. And I know Adam will say it's not working at the moment because we blocked the decanter before I finished. And I think BC, you're highly involved in networks at the moment. And you're involved in 5 cost actions. And I know I'm involved in cost actions, and that's time consuming but necessary to build networks. You're also, as the last speaker said, you're involved in the BBSC RC Networks Industrial Technology and Food Waste Net, and also LIMNET. So then this is the Low Impact Materials Network, and again that's A for B knowledge, and that's led by BC. So networking is key, and that gives you opportunities in biometrics, smart materials, 3D printing, and low carbon construction, core BC areas. So with that, I'd just like to say happy 25th anniversary. See you all in 2039 for the 50th. I'll be 81, but I'll be there. And that's me. Okay? Thank you.